Okay, we were up to looking at the effect of adding sodium hydroxide. So sodium hydroxide will react with my acid, decreasing the concentration of H+. So adding sodium hydroxide reduces the H+ concentration. So the equilibrium is going to want to oppose that change. It's going to minimize the loss of H+ by producing more H+. So how do I get more H+? Well, if I react these two together, these two will react together to make these two, which will increase the concentration of H+. So by removing this, I encourage the backward reaction to happen, which means that I shift the equilibrium to the left and I produce more reactants. So when I say reactants, I'm always referring to the ones on the left as the reactants and the ones on the right as the products. Otherwise, if you start thinking, well, if I'm going backward, these are the reactants and these are the products, then it gets too confusing. So I'm always going to refer to the ones on the left as the reactants and the ones on the right as the products, regardless of which reaction I'm talking about, the forward or the back. Okay, so you should have got that situation there. Okay, right, let's go on to change number 2. So change number 2 is a change of temperature, and you should have seen this equation when you were reading the textbook. So the important thing now is that we are looking at this piece of information here. So the enthalpy change for this reaction is positive, which means that the forward reaction is endothermic, as in it absorbs heat energy. And the reverse reaction is exothermic, which means that it releases heat energy. So again, we're going to just look at two situations. So situation A will be what happens if I increase temperature. Well, increased temperature will increase the heat energy of the system. So what will the equilibrium want to do? It will want to move in order to minimize that increase of heat energy in the system. So you think about the heat energy in the system is increasing, so the reaction wants to absorb some of that heat energy to minimize the increase in heat energy. How can it absorb heat energy? Well, it can do the endothermic reaction. So it will, the equilibrium will move to minimize increase in heat energy, which means that it will shift to the right. Okay, and if it shifts to the right, it's going to make more of these over here. Okay, so it produces more products. So if I wanted to, I don't know why, but maybe I wanted to get as much water as possible out of this reaction, I would increase the temperature. Okay, so now if we look at B, okay, so B, I'm going to decrease the temperature. How is that going to affect my reaction? So you need to now have a go at that one. Fairly straightforward, just what we've done previously, but the opposite way around. Okay, so you should have got that the decrease in temperature will decrease the heat energy of the system. The equilibrium is going to want to move to minimize that decrease. It can do that by doing the exothermic reaction, because that's going to release heat energy into the system. So if it shifts to the left, favoring the backward reaction, then we will produce more reactants. Okay, and carrying on, we've now got our final one, number 3, which is our change of pressure. All right, so when we look at change of pressure, these are now gases rather than concentrations, which would be for solutions. we need to look at the number of gas particles. So over here on the left-hand side, 2 moles of gas molecules. And over here on the right, I've got 1 mole of gas molecules. So you can imagine if it was a situation where it was just one of these gases, so if it was just NO2 gas, or if it was just N2O4 gas, which one would have the higher pressure? Well, the volume's the same, but over here we've got more moles of gas, so this would give us a higher pressure, this would give us a lower pressure. So again, the same analysis, we're going to do A, which is to increase pressure. Now if I increase the pressure, the equilibrium moves to minimize the increase in pressure. Okay, so how can it do that? Well, it's going to want to try and lower the pressure, and we just said the pressure over here is lower, so it's going to shift to the right, reducing the number of gaseous moles. And by doing that, it's going to produce more of this product. And you can now, I think we've done enough of these, so for B, you can have a go at that one yourself, decrease pressure. So it should be fairly obvious by now what that's going to be. Okay, and so that's all the situations you need to know about. The last thing we're going to talk about just for a couple of minutes is the Haber process, okay, which combines the effect of temperature and the effect of pressure. So we can see over here that we have got a negative enthalpy change, which means our forward reaction is exothermic, our backward reaction is endothermic, and also on this side of the equation we've got 4 moles, and on this side of the equation we've got 2 moles. So the question is, which conditions would give us the maximum yield of ammonia? Okay, so pause it now, have a little think about that. How would I maximize the yield of ammonia? Right, so you should have been able to work out that low temperature, because a low temperature is going to decrease the heat energy in the system. The reaction wants to increase the heat energy in the system. It will do that by doing the forward exothermic reaction. And you should have also worked out that it would be high pressure, because a high pressure, the equilibrium will move to the right where there are fewer gas molecules to decrease the pressure. Okay, now that's all great and everything, but Haber, he needs his ammonia today. Okay, so having a low temperature means the rate will be slow, which is not good. Also, Haber at the moment, he's only just started his ammonia producing business, and he can't afford the expensive equipment that you need in order to be able to do this at high pressure. So those are the problems that you would have. So when we do the Haber process, you have to come up with a compromise between these two situations. Finally, we can also add a catalyst. In the Haber process, we actually use an iron catalyst. And the catalyst has no effect on position of equilibrium. No effect at all. Because the catalyst increases the rate of the forward reaction and the backward reaction. So it allows both of those reactions to happen quicker. All right. But what that means is, it means that the reaction can be done at a lower temperature because the catalyst is increasing the rate.